Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Our speaker is Ashish Goel from Stanford University. He's a professor there in Management Science and Engineering Department. And he has been here earlier. And his interests are mostly in algorithm design, analysis, and application. And today he'll be presenting a talk on simultaneous optimization and fairness.
Thanks, Kamal. So this is joint work with Adam Meyerson from UCLA and Sang-Woo Cho from USC. And I'm going to focus a little bit more on the definitions, a little bit less on the longer proofs. I'm going to skip the longer proofs. Please feel free to interrupt me as often as you want to. So here's an example of what I mean by fairness. So imagine you're given a pie and Mrs. Robinson has 4 children and she wants to split the pie fairly. And what should she do? I mean, the children are the same size, conveniently named A, B, C, and D. So she could just chop the cake in 4 parts and give 1 slice to each. So in this case, splitting the pie fairly was fairly easy. The question is, what happens if there are more constraints? So imagine Alice and Eddie only want apple pie. Frank is allergic to apples. Kathy wants equal portions of both pies because she likes to have like 1 bite of this and then 1 bite of that. And David wants twice as much apple pie as lemon. Right? And now you come up with an allocation. So Mrs. Robinson come up with some allocation of these pies to her kids. And the question is, how do we measure the goodness of an allocation? Right? So I'm going to talk of this problem mostly. When I say goodness, I mostly mean fairness. Right? But another way of thinking about it, for those of you who know utility theory, you could think of it as social welfare. Right? So you have a centralized planner like Mrs. Robinson, and this is her society, and she wants to split some resources among this society. And the question is, what's the right social welfare function to use? Okay. So here's the problem in a little bit more formal problem. So imagine that you are given some resources, and let's say x equals x1, x2, xn denotes the allocation of this resource to n individuals. And you're given some constraints. So for this talk, I'm going to assume that the constraints are x greater than or equal to 0, so no one is going to get anything negative. And I'm going to assume that x comes from S, so this set of feasible allocations comes from S, where S is convex. So the set of allocations is feasible allocations forms a convex set. And even if the set is not convex, many of the things I'm going to talk about will go through. And let us say Ux is the total revenue or the total utility from the system, or let's say the total social welfare, and then the goal is to maximize U of x subject to x is in S. So one example is you want to allocate bandwidth to n users in a communication network, and in that case your capacity constraints would be Ax is equal to C. Another example would be you want to allocate water to farmers, which is a big problem in California right now, and you want to do it fairly. So as soon as I pose this problem, right, especially if I pose this problem in the context of say farmers in California, if you knew the utility function u, it's very clear what to do. Right? I mean, given a function u, it can't be that hard to optimize. Right? In the worst case, you could do some form of exhaustive search. Right? The question is, what's the right utility function u? And some of the standard assumptions are that u is concave, so that corresponds to the law of diminishing returns. And that u is non-decreasing, so more bandwidth or more water can't harm, right? So I'm going to further assume that the utility function u is such that u0 is 0, and that u is symmetric in x1, x2, xn. And this fact that u is symmetric in x1, x2, xn essentially means that the social planner is indifferent to the identities of the individuals, right? So you could take, instead of giving 5 to one and 15 to the other, you could switch it, and the social planner would think that this new allocation also has the same utility. No, it's the same thing, right?
How could you switch it?
So the social Mrs. Robinson doesn't discriminate between Alice and Kathy. It's Alice and Kathy which have different constraints. Right? So you can have a symmetric utility function, but you can have asymmetric constraints. And then the solution will not be asymmetric. Yeah, that's essentially the point of the talk. What's the right utility function, right? And so if you knew all this, the corresponding optimization problem is easy. You have a convex feasibility set, you have a concave objective, you can use any standard techniques to solve it. The question is, what if U is not known, right? Or if there's some dispute about U, which there definitely is in the case of farmers in California, right? So, so yeah, you can think of it as welfare, utility, fairness. They're all concave, right? They're all, yeah. Sorry? It depends on all the users, yes. So U is a multivariate function, so it depends on all the users. Yeah. So, so the interesting question is, what if U is not known, or if there's some dispute about it? And so simultaneous optimization is concerned with maximizing U of x simultaneously for all canonical utility functions U. And I'm going to call something canonical if U0 is 0 and U is symmetric in x1, x2, xn. Right? So the point of this exercise, the point of this talk is not the constraints or not the optimization itself. Is this thing about what U ought to be and what the class of appropriate U's is and how do you optimize over this class. And clearly this is, I mean, even as soon as I write it, right, I mean, you should disbelieve this because clearly this is not going to be possible. So you can't maximize U of x simultaneously for all canonical utility functions U. Right? But so let's suspend disbelief for a minute and let's see, why do we want to do this simultaneous optimization? The answer is that often the utility function is poorly understood. So you want to do customer satisfaction, right? Now what is customer satisfaction? Who tells you what customer satisfaction is? It seems reasonable to say that customer satisfaction is concave, right? But it follows the law of diminishing returns. Or that if you give someone more bandwidth, they are not going to be unhappy. But beyond that, how do you capture customer satisfaction? Right? And often we want to promote several different objectives. So if you want to do fairness, then should we maximize?
You look at the sort of customer satisfaction jointly observed by me.
Yeah.
It's sort of clear it could be convex for myself and convex person. But it's not that clear that it should be jointly convex. I assume that you say convex, you really mean a convex function or that.
Concave, yeah. Yeah.
So that's not so clear, right?
Yeah. So maybe for customer satisfaction it's not so clear. But for fairness or for social welfare it's much more clear. Right? And I'm going to illustrate why, at least I think it's clear. Yes.
But it's true.
Yeah.
If you give him more, if there's some, if it's a zero-sum game, then I get less. But fairness, you're taking that into account.
Yeah. No, yeah, if I give him more, you may or may not get less, yeah, but you definitely you have to, but concavity only holds, concavity is only relevant if you hold the total amount fixed, right? So concavity only talks about you take your two values and you take their average and then what happens. So the question, yeah. So let's think of fairness for a second. Should we maximize the average utility? Is that what fairness means? And by the way, this is a capitalist objective, right? You're given some economic system or some social welfare system and you want to maximize the average utility, which is the same as the total utility. Right? Do you want to be...
Is it like Bush capitalist? I don't think so.
It's like it's efficient. Maybe not capitalist, but it's a system which wants to promote efficiency. So if you have a system which wants to say we want to derive the most efficient, we're given some set of... Yeah. So, or do you want to be maximum fair? So being maximum fair is like stealing from the rich. So if you see someone who's richer than you, then it's their fair game. You can go and steal from them legally. And whatever you converge to is called maximum fairness, right? And in some sense you could say that maximum fairness corresponds to the socialist objective. Right? So there's this tension between do you want to maximize the capitalist objective or the socialist objective. And there are these other things that you see in the newspapers all the time. Like you want to maximize the average income of the bottom half of society, right? Like you always see this whenever there's this tax thing, you see the bottom 50% is only getting like 5% of the rebate and the rest of it is going to the top some percent. Or maybe you want to minimize the variance, which is also like a concave problem because variance is convex but you want to minimize it, right? But really the right thing you would love to do in an ideal setting is to do all of the above, right? So if in a country you could do all of the above, then no one can come and point fingers at you. Not necessarily, but that's definitely, it's not necessary, but it's not that far. I mean, yeah. Well, if I take,
not true that nobody will complain.
That's also true.
Particularly the rich will complain.
Sorry?
There's that nobody. It's not. I mean.
Yeah, somebody will complain.
I don't mean it sort of. I just say it's not sort of regret-free for everyone. It's just that you might say everybody might agree it's socially regret.
That's true. nobody would complain a priori. So what I mean by nobody would complain, so there's this notion of called the veil of ignorance due to this economist called Rawls, or maybe philosopher called Rawls. And the idea there is that he gives you a scheme and you have to sign off on the scheme without knowing which individual you're going to be in the scheme. So if you could, so it's called the veil of ignorance. So you are subscribing to the scheme. If you sign off on the scheme, you will be like a random guy in that scheme. The question is, so somehow, so nobody would complain in that sense. If you give for a Rawlsian allocation, nobody would have a philosophical objection to something which could maximize all of these at the same time. They might have a personal objection because they get less money. So what does this have to do with fairness? So consider the following three allocations of bandwidth to two users. Right? In the first case, you give A to the first user and B to the second. In the second case, you give B to the first and A to the second. Right? In the third case, you give the average to both of them. Right? And now if measures fairness, then intuitively it seems like f of AB should be f of BA. Right? I mean, in one case you give 5, 15, in the other case you give 15, 5. And it should be less than or equal to f of A plus B by 2, A plus B by 2, which is the case when you gave both of them 10. So intuitively, informally, it seems like if f measures the fairness of an allocation, then f is symmetric. That corresponds to saying f of AB equals f of BA, and is concave, which corresponds to saying that f of BA is less than or equal to f of the average. Okay. So, and then I'm going to, if I also assume f0 equal to 0, and I also assume f is non-decreasing. So f is non-decreasing essentially says that if I can give more to Paul without robbing Peter, then that's a good thing to do. Right? Then if I can increase, instead of B, I can make this B plus 1. That should only be better, right? Because I'm not taking it away from it. So essentially, all the fairness measures we found in literature are equivalent to maximizing a canonical utility function. Right? So if you could do simultaneous optimization, then you would also be fair under all notions of, all reasonable notions of fairness. Right? But of course, you wouldn't be able to do it.
Are you claiming that if you do the same thing for three variables, you can still prove it? I guess the concavity you just put in. I mean, you just said intuitively and then you put.
No, so this corresponds to concavity. So this is exactly the definition of concavity. So it's in particular, yeah. So stealing from the rich is concavity, yes. But only if you keep the total allocation fixed. If you steal from the rich, in the process you introduce some inefficiencies, then you can have a concave function and you cannot say which way it's going to go. So here are some more examples of canonical utility functions. Min is a canonical utility function. Pi of x, which is the amount allocated to the I poorest users, is a canonical utility function. Sum and average are canonical utility. If f is any univariate utility function, which is like 0 at 0 and non-decreasing, then sum over all I f of xi is a canonical utility function. Right? So entropy, sum over I log of 1 plus xi, etc. Variance is symmetric convex, but you typically want to minimize variance, so that's also symmetric concave. It's like maximizing some symmetric concave function. And we can obtain, we'll be able to obtain slightly weaker guarantees if f0 is not equal to 0. So all these requirements were reasonable, like concavity is reasonable, symmetry is reasonable, non-decreasingness is reasonable. But f0 equal to 0 was somehow ad hoc, somewhat ad hoc. Right? So if f0 is not equal to 0, we'll still be able to obtain slightly weaker guarantees. So also obtain so this will also apply to functions like summation over I log of xi, which is a pretty special function, I'll point it out later, and hence also to functions like pi I xi, which is just the exponential of this function. Okay. And so I'm defining all these things, right, and it seems very nice, but the reason is because it's too good to be true, because obviously you can't do all of these things at the same time. Right? So, but still let's keep going. So, I'll now define this notion called majorization. So suppose x and y are two n tuples of positive reals. And like I said before, I'm going to define pk of x as the sum of the k smallest numbers in x. So I'm going to call them the prefix functions. And I'm going to define sk of x as the sum of k largest numbers in x. And by the way, pk of x is symmetric because it doesn't matter what order x is arranged in, you're going to take the k smallest numbers. And it's not hard to see that it's also 0 at 0, non-decreasing and concave. So let's focus on these prefix functions. We'll say x is majorized by y, and we'll denote it by x less than this funny less than y. If for all k, pk of x is greater than or equal to pk of y, and for the final prefix, the two are the same. So, so what does it mean pk of x greater than equal to pk of y for all k? What it means is that the bottom half, say k is equal to n by 2, then the bottom half of society in x is at least as rich as the bottom half of the society in y. The poorest guy in x is at least as rich as the poorest guy in y. The 10 poorest guys in x together are at least as rich as the 10 poorest guys in y. Okay? So that is x less than y, x majorized by y. And the funny thing is here I am saying greater than equal to, but here x is somehow less than y. But there's a reason for that's just a notation that's been around for 100 years. I'm just sticking to that notation. So the premise is that x implies x is majorized by y is the same as saying that x is fairer than y. Okay? And this statement informally was stated by Lorentz in 1905. It was somehow formalized by Hardy, Littlewood, and Polya in 1929.
What context did we look at this?
So Lorentz was looking at fairness, and Hardy, Littlewood, and Polya were looking at inequalities. And so this whole prefixing was proposed by Lorentz as a measure of fairness. And these are called, in economics, these are called, I think, Lorentz indicators or something.
But with Hardy, Littlewood, and Polya,
They didn't like applications.
yeah, but okay. So what does it mean that x is fairer than y?
So this was Lorentz's premise. So,
I see.
so Lorentz said that.
So Lorentz defined the notion of fairness, and Hardy, Littlewood, and Polya proved
Some sort of formal theorem
something
somehow.
about partial orders implies that whatever that definition.
Wait,
is.
Yeah.
I don't understand. I thought this is just a definition. What does it mean that x is fairer than y?
No, this was
defined it.
this is what Lorentz said, right? It's like 1905. We can't.
So how
he-
Littlewood just introduced this partial order?
No, so Lorentz wrote down these prefixes, and he informally defined the partial order, and he said this is what, if this is true, then x is fairer than y. He proposed this as a measure of fairness.
So what did Hardy?
Yeah, okay, let me get to what Hardy, Littlewood, and Polya proved. I'm not going to assume x1 less than equal to x2 less than equal to xn, so please ignore that line. I was going to take it off, but I forgot. So let me first illustrate what majorization really means. So what majorization really means is that suppose x is majorized by y. That means if you plot all the prefixes of x against k, so this is the, for any value of k, this is the k prefix of x, this is the k prefix of y. They have to both start at the zero at the same value because p0 is 0. I mean the 0th prefix is 0 for everyone, and we said that the nth prefixes are the same. So saying that x is majorized by y means that x is always above y when you plot the prefixes, and x is always below y when you plot the suffixes. And in the end they match up. And the theorem that they proved was that if x is majorized by y, if and only if g of x is greater than or equal to g of y for all symmetric concave functions g. So this was there somehow, but they weren't really trying to prove anything. They weren't really trying to do fairness. They were just interested in inequalities. Because I've been told by many people that Hardy didn't like motivation, so they were just interested in proving theorem. And this also says why there's this mismatch between less and greater than equal to, because they were interested in proving inequalities about convex functions. So in their notation it makes sense, because what they would say is x is majorized by y if and only if fx less than or equal to fy for all symmetric convex functions. Right? So that's how they prove the theorem.
So if x equals y, then x is also small.
Yes, yes. Right. Sorry. So maybe I should have been.
I didn't mind this all of this. I didn't mind this.
Okay, sorry. Yeah, it should have been less than equal. I just didn't know the LaTeX notation for less than equal. But I'm sure one exists. I'll figure that out. So the intuition is x is majorized by y if and only if you can write. So the intuition for the theorem or the summary of the theorem is that x is majorized by y if and only if x is equal to dy for some doubly stochastic matrix D. So you can go through the definition of majorization, and that's essentially what it's saying. I mean that's what, because they have to match up at the end, so you know the sum has to be the same. So that gives you the doubly stochastic. But doubly stochastic matrices essentially take generalized averages. That's what doubly stochastic matrix does. And therefore, if you take a generalized average, an average can only increase a concave function, so that means that it can only increase symmetric concave functions. So this is a summary of the proof. And so the sorry.
It's only one of the two ends.
If and only, I'm saying this is the intuition The intuition.
Oh, the other one is trivial because it just applies to S.
Yeah, for example.
Okay. Okay. Yeah. Actually, sorry. Now I understand what you're saying, and that's exactly right. The other one is trivial because you just apply it to S and P because they're symmetric. Yeah. One direction is trivial because exactly what you said. So what the implication is that a most majorized vector simultaneously maximizes all symmetric concave functions, but we are still like in the land of hopes and dreams because this thing is not going to exist, right? So a most majorized vector may not exist, and the relation majorization relation defines a partial ordering and hence may not have a minimum, right? And just to contrast it, there are other, if you have a specific utility function, then of course the thing will be defined, right? So maximum fair solution always exists because it's the maximum under some lexicographic ordering. And we know that if you want to maximize min, it always exists and so on and so forth. Yeah. So what we do then is introduce this notion of approximate majorization. So let me say that let's say pi star is the largest feasible value of pi. So you're given some constraints, x is in S, and under those constraints you define the largest possible value of pi of x and call that pi star. So I'm going to say x is alpha majorized if pi of x is greater than or equal to pi star by alpha for all I. Right? So for every I, this is a variant of the notion of majorization, and the interpretation is that if you look at the k poorest individuals in the allocation X, they are collectively at least 1 over alpha times as rich as the k poorest individuals in any other feasible allocation. Yeah? Right. Okay. It's going to become.
Thought of doing that.
So. And so you can define something called, instead of alpha majorization, you can define something called alpha balance in terms of the suffixes, but I'm not going to go there. Yeah? So you can define it and make sense, but here's what it means now. So if I take x and I multiply it by 2, then if the prefixes are always above y, then I'm going to say that x is 2 majorized, right? And similarly, if the suffixes are, if I divide it by 2 and the suffixes are always below y, then I'll say it's 2 balanced. But in this talk, I want to focus just on 2 majorization. So why is this useful? So it's useful because of the following theorem. We can say that an allocation X is alpha majorized if and only if U of X is an alpha approximation for all canonical utility functions U. So, so if I could just, so remember this alpha majorization is defined only in terms of these n functions, the n prefix functions, right? But the class of canonical utility functions is infinite. In fact, it's uncountable, right? So, what we are saying is alpha majorization results in approximate simultaneous optimization. So, or another way of thinking about it is the n prefix functions are complete for the class of canonical utility functions. So if you could approximate just these n functions, then you're approximating the whole class. So now the problem starts to look a little bit tractable from an approximation point of view, right? You don't have to worry about all the utility functions, you have to just worry about these n functions. So, and then similar guarantees exist for alpha balance and minimizing all symmetric convex functions, but I'm not going to go over those.
So wait a second, I'm not understanding the fact that the n prefix functions are complete.
Yeah.
What does that have to do with the approximation?
So earlier if you try to do approximations, it wasn't clear how you can approximate all the functions in an infinite class. But now you're given just these n prefix functions. So now if you could just approximate these n prefix functions, you are done. So hopefully you're left with an easier problem. Hopefully, maybe not, but hopefully you're left with an easier problem. So here's the proof of theorem 1. I said I'm going to skip all the hard proofs and give only the easy ones, right? So this is the proof of theorem 1. So let's assume pi of x is greater than or equal to pi of y by alpha for all I, and let's say for all y. Right? So x is alpha majorized. So I define z as alpha times x. Now if z is alpha times x, then I can keep, then the following operation is key. If z is alpha times x, then I can iteratively reduce the largest components of z to obtain a w which majorizes y. Okay? So pi of x is greater than or equal to pi y by alpha. There's no majorization relation necessarily between x and y, but if I take z equal to alpha x, then all the prefixes of z are larger than all the prefixes of y. And then I can iteratively start reducing the prefixes of z to obtain some w which exactly majorizes y. So once I obtain this W, then let me look at any canonical utility function f. So I know f of x is greater than or equal to f of z by alpha plus f of 0 times 1 minus alpha. That follows by concavity, because I can write x as z divided by alpha plus 0, sorry, it should be 1 minus 1 over alpha plus 0 times 1 minus 1 over alpha. Okay. But f0 I assumed is already 0, so therefore f of x is greater than or equal to f of z divided by alpha. But then because the function is non-decreasing, right, and I obtain w by reducing z, I get fz by alpha is greater than or equal to f of w by alpha. But because w is majorized by y, I get that's greater than or equal to fy by divided by alpha. Right. So it's true. So now it's true that for any canonical utility function, so I essentially proved the theorem that if you have alpha majorization, then you have an alpha approximation for all concave functions. Okay. And this part, this is the crucial part which follows from, which comes from Hardy, Littlewood, and Polya, that if w is majorized by y, then this condition holds. Okay. So as it turns out, you can relax this class further. So earlier I was assuming that u is symmetric, concave, non-decreasing, and u0 equal to 0. But if you don't make this assumption, u0 equal to 0, then so one example of this, the main reason why I'm interested in this is because of this function, maximize summation over I log of xi. This function is symmetric, concave, non-decreasing, but it's not 0 at 0. And the reason is because this is the solution, this function represents the Nash bargaining solution, which is something which is axiomatically derived. So Nash gave some axioms of fairness in the context of the individuals who are bargaining with each other, and he said this is the right function to optimize, subject to whatever constraints you have. Okay? So even if you have functions of this form, we end up getting what I call a resource augmented guarantee. So what you end up getting is not that u of x is greater than or equal to u star by alpha. What you end up getting is u of alpha x is greater than or equal to u star. So if you are only given alpha times more resources, then you could be as good as the optimum. Right? This is slightly weaker guarantee. Okay. So now this definition is fine, but the question is, does it exist, right? So next theorem says that for the bandwidth allocation problem in networks, there exists an order log x majorized solution, and in fact this can easily extend to all convex problems. Right? In fact, you can even think of this as if the feasibility set S is convex, there exists an order log x majorized solution. I haven't defined what x is. I'll do it in the next slide. I just want to say it's order log x majorized. And so what we're really saying is we can simultaneously approximate all canonical utility functions up to a factor of order log n. And these results extend to, I already said that, arbitrary linear programs, arbitrary convex programs. So what is this x? So let me, like I said before, just to remind you, pk star is the largest possible value of pk for a given problem, and let's say alpha star is the smallest possible value of alpha. So is the most in approximate majorization is the smallest possible, the best approximation ratio you can obtain, and let's say x star is a feasible alpha star fair solution. Okay. So I'm going to define the inherent imbalance of a problem as Pn star divided by n divided by P1 star. So what is Pn star divided by n is the largest possible average benefit in the system, right? What is P1 star is the largest possible minimum benefit. So the ratio of the two, you can think of it as the gap between, you're given some set of constraints, and under these set of constraints you want to run a socialist economy and a capitalist economy, and the two of them are going to have some difference, and that ratio is what I call the inherent imbalance. Okay? So if you're a capitalist economy, you could have given everyone $10. If you're a socialist economy, the poorest guy would have gotten $1. So you look at this ratio of 10 to 1, and that's your inherent imbalance, right? And that comes from the set S. Okay? So the set S determines what the inherent imbalance is. And this often goes polynomially or even slower in the problem size. So this is the existence theorem. I think I should skip the proof. So suppose a set of feasible allocations is convex. Then the theorem says that alpha star is less than or equal to some constant plus some constant times log of this inherent imbalance. Right? So I'm not, sorry, let me just skip the proof completely. It's not that useful. So, but the theorem is that alpha star is order of log of the inherent imbalance, and this function is this proof is non-constructive. So we already saw that approximate majorization captures simultaneous approximation, and we saw that an order log x majorized solution always exists. Now the question is, can we find this majorized solution? Can we efficiently find it? right? Just because it exists, it might be too hard to find. It might be NP complete, and then we'd have to do another approximation, so it doesn't make sense. It's not clear what we are saying. Okay? So theorem 3 says that given arbitrary linear constraints, we can find in polynomial time the smallest alpha such that an alpha majorized solution exists, and we can also find the corresponding alpha majorized solution. Okay? And in fact, we can also do it for convex programs if the original convex program is tractable. Yeah. So so I'm not going to give the whole construction for the whole algorithm for finding it, but suppose we just want to compute pk star. Okay, so just this will give you all the intuition about how to compute alpha star. Suppose you want to compute pk star, so you want to find the largest possible value of the prefix pk. So you would write a program. You can write a program which says maximize pk subject to ax as n equal to c, which was your original constraints, and subject to saying that for all permutations sigma in the symmetric group of n, pk is less than equal to x of sigma 1 plus x of sigma 2 all the way up to x of sigma k. Okay? So what does it mean for something to be the kth prefix? It means that the k poorest guys, the pk can be at most what you give to the k poorest guys. But if you take all permutations, there will be one permutation which will be the sorted permutation, and that permutation would impose the right bound on pk. Right? So the explanation may be constraints, but detecting a violated constraint is very easy. So how will you detect a violated constraint? Given a candidate solution, you would just arrange all the x's in increasing order. Once you arrange them in increasing order, you know that's the permutation that's going to violate the constraint, if any, and you just check for that permutation. And so either that permutation satisfies the constraint, in which case there are no violated constraints, or it doesn't, in which case you have found a violated constraint. Okay? So as it turns out, then you can use this notion of a separation oracle to solve this linear program in polynomial time, right? And the separation oracles are powerful enough to handle arbitrary convex programs. So if instead of ax as n equal to c, this was just some convex set, x is in S. As long as you were given a separation oracle for that set, right, you'd still be able to solve this thing in polynomial time. So some of the extensions are we can extend, so and then you can use similar techniques to find alpha star. So as an extension, you can impose fairness as constraint. So you can say I want to maximize, I have some other objective I want to maximize, right? But I also want to win the next election, so I don't want to be too unfair. So you can impose fairness as constraint. You can say alpha is less than 20. So I want to say I don't want to piss someone off so much that they don't vote for me. Subject to that, I want to maximize something. I don't want to say what something is because that seems like a political statement. But you can do that. You can also obtain a smaller LP. In fact, you can obtain a polynomial size LP for this problem. But that polynomial size LP is not interesting. This is somehow much more interesting than the polynomial size LP. And this extends to general convex programs, like I said, extends to alpha balance, even though I'm looking for alpha majorization here. Okay? So now that I've given this whole thing, I think I should give some history. So recently, I mean, in more recent times, not in times of like Hardy-Levin and Polya, they started with prefix-competitive algorithms for scheduling, like Kleinberg, Rabbani, and Tardosh, which are essentially trying to do some sort of alpha majorization. And then we did the same thing for online algorithms of fair bandwidth allocation, and then Kleinberg and Kumar extended to some combinatorial problems. But the thing was, in each of these papers, we are trying to solve roughly the same problem in an ad hoc fashion, but we didn't know about this notion of majorization. So you're like trying to prove half a theorem here and half a theorem there, or we had algorithms, but we didn't actually know what those algorithms were really doing. And then finally, I talked to David Shea at Berkeley, and then somehow everything clicked together, and then we realized that this is actually connected to all this simultaneous optimization. And then we did then we extended this framework for stochastic load balancing and integer programming, and recently Bookbinder and now gave improved online bounds. So I'm going to give 3 illustrations. I'm being ambitious. I'll try to at least give 1 or 2 illustrations. So the first illustration is distributed bandwidth allocation in a network. So I want to show how this framework actually applies in concrete settings. So the first thing I want to do is distributed bandwidth allocation in a network. Then I want to go to job allocations to 1 infinity machines with non-identical job sizes. And then I want to talk a little bit about scheduling of stochastic jobs. Sorry? The cake? Yeah. Yeah. Okay. Yeah. I'll get to that. I don't have a picture, but I can get to that visually or verbally or on the board. But it's actually it is going to make yeah. Okay. I'll get to the cake in a few slides. So So distributed bandwidth allocation is a special case of resource allocation. We are given n source destination pairs. So I'm going to think of a source destination pair as a flow. We are given fixed routes, and let's assume that every source destination pair is a fixed route, like in the internet. The route is fixed, and then you are running TCP on top of the route. I'm going to assume that the identical capacities on edges, and all this is for simplicity. You can reduce these, you can remove these assumptions if you like. And the goal is to find a distributed bandwidth allocation algorithm so that all canonical utility functions get well approximate. Right? So the key thing here is distributed. In a centralized setting, you can do all this. You can solve these LPs, and you can find whatever you want. But one of the reasons we got interested in this problem is because there was a series of very nice papers by Kelly, which did distributed bandwidth allocation for a specific utility function. And the question then was, can you get a distributed bandwidth allocation algorithm which is good for all, somehow good for all utility functions? So this word distributed here is important, right? So, and the basic idea in almost all distributed bandwidth allocation algorithms that I know is to have a primal-dual algorithm, right? And this is along the lines of Gert Koneman or Totnish-Tardosh or say Kelly, Maulo, and Tan. And the idea is each flow agent adds flow incrementally. So you can think of each flow agent, or think of it as each sender-receiver pair has some primal variable xi, which they are incrementing or decrementing, and each edge maintains a dual price, or is also sometimes known as a shadow cost, and that's what I'm going to call LE. Okay? And once you have these things, the dual price is only on the edge, and this dual price is not a real price, it's not a real cost, right? It's just something artificial. The primal variables are the real variables. So you can define a dual price Wi for each flow as the sum of the dual prices on all the edges in the route, right? So if this edge has $5 and that edge is 10, then you can say the dual price for the flow is 15. Okay? And I can also define a primal flow XC for edge E as the total flow on the edge. So this is a natural setting, and here's the algorithm, and the algorithm is actually really simple. It's actually much simpler than trying to solve the LP that we had originally. And so initially each edge has some price. Let's say LE is equal to gamma. So each edge has some price, and this price is somehow small. And in each iteration there's a primal update by each flow agent, followed by a dual update by each edge agent. And the primal update rule for each flow agent is very simple. It says if Wi is less than 1, then increment xi by some small number epsilon. Okay? So if my total dual cost is less than 1, I'm going to increase. Otherwise, I'm going to stay where I am. Okay? And the dual update rule for each agent is that you just look at the total new flow that was introduced. So delta xc is the new flow that got introduced in this update iteration. You multiply LE by 1 plus beta times the new flow. Okay? So this is the flows are updating additionally, additively, and the cost is updating multiplicatively. And this is known as a multiplicative update rule. And all the primal dual algorithms, at least all the ones that I know of for bandwidth allocation in the last 1.5 decades, essentially use some form of multiplicative update. So this algorithm is not new, and it's not complicated, and this algorithm is actually simpler than the ones which exist, right? So the point here is not the algorithm. I don't want to say that this algorithm is somehow great, right? Because it's actually, that's what everyone was doing, and everyone was actually doing things which are smarter and harder and more difficult. Right? So the interpretation here is because these dual prices update multiplicatively, you can think of the dual prices as exponential. So let's say A and mu are some parameters, and let's say lambda E is the fractional link utilization. Okay? Then this is the same as saying that dual price is exponential in the link utilization. So as the link utilization increases, your dual prices increase exponentially. And then the theorem is that for appropriate parameter choices gamma, beta, and epsilon, the final flow bandwidth vector is feasible and is order log n majorized. Right? So if you just run this rule where everyone keeps updating their primal flow till they hit some cost ceiling and then they stop, then what you end up getting is a feasible bandwidth vector which is order log n majorized. And you can modify it very slightly to make sure that this terminates in polylogarithmic iterations. So it's going to terminate really quickly, and it's going to terminate with the order log n majorization, and you can actually prove that this is the best you can obtain. You can't actually obtain better than log n majorization for this problem. And let me tie this to this cake example. Right? So the cake example is the following. So you're given these cakes which are say arranged on a buffet table, right? And Mrs. Robinson's rule is the following. Initially she says all cakes are free, okay? And she gives everyone like all their kids a very tiny spoon, and she she says initially all the cakes are free, and she gives them each $1. And she says you can go to this cake stand and you can fill up your spoon whatever way you want, as long as the total price of the cakes you pick is less than $1. And they take their spoon, they go and eat that spoonful, and they come back and get in the line again, right? But when they get in the line again, Mrs. Robinson looks at her cakes and she says, oh, the apple cake, like 4 spoons of apple cake disappeared, but only 1 spoon of lemon cake disappeared. So the next iteration she'll say, oh, now an apple cake is expensive. A lemon cake is still cheap, but an apple cake is now like 20 cents. And again, these students are going, all the children are going to go with this, teaching too many classes. All the children are going to go with their small spoons and with $1. Every time they get in the line, she gives them a spoon and $1. And all these kids are going to go through the line with the spoon and the $1, and they'll fill their small spoon with whatever cake they want. She doesn't even have to supervise it, right? That's why it's distributed. She doesn't have to supervise it. And then at the end, they get out at the end and they show her the spoon, and she says, yeah, your spoon costs less than $1. Give me $1, go eat your spoonful, come back, get in the line again. At some stage, this guy who wants apple, twice the amount of apple pie as lemon, will find that apple is too expensive. He'll get to the line. Mrs. Robinson will say, you are now costing me more than $1, so go away. Right? So this dollar is virtual, and at the end, whoever is left will keep eating. Ultimately, all the cakes will become so expensive that no one can eat anymore, and at that time you will stop, and she'll say, okay, you got 5 spoons, you got 10, you got 20, and that will be approximately majorized solution. So this is roughly what it corresponds to, right? And somehow.
And now sort of the first. Now I can sort of eat the remaining.
So the remaining is somehow the trick is the right thing to do would be to tune these costs in such a way that there is nothing remaining.
So you say the richest person only gets log n as much as everybody else together?
No, it's possible that the richest person might actually get almost everything. So it's like if you can give more to Peter, yeah.
Why is it not log n?
So if you can give more to Peter without robbing Paul, that's actually good. So I mean the richest person wants, maybe the richest person is the only one who wants like meat pot pie stuffed with turkey and something else, right? But everyone else wants lemon cake and apple cake. So like everyone else will fight for the lemon cake and the apple cake, and then this richest guy can get the whole turkey meat chicken pie. Sorry. So it's so there's no, so you're only comparing the poor people to what they could have done in some other allocation, right? You cannot, a poor person can't come and say that guy is getting 100 times more than me, because maybe that guy is really efficient, right? All a poor guy can come and say is, okay, the 10 of us together, the 10 poorest guys of us together could have gotten so much more, and you're giving us so much less. So essentially that's the same as saying someone on Social Security can't say that Bill Gates is earning so much more than me, right? Someone on Social Security can only say that there's a way by which these guys on Social Security could have gotten $20 more, and you're not giving us those $20. But I'm still not satisfied with this distributed algorithm, and for the following reason. The previous slide gave an algorithm, it was not really a pricing based protocol, right? So the important thing here was that Mrs. Robinson started with 2 complete cakes, and then they start from the beginning, right? But the way, if you want to really think of this as some sort of a pricing based protocol, say water in California, tax rebates and so on, you start with some state of the system, right? And you, like in the stock market, you start with whatever state you want, and ultimately the market will clear, right? And it's all pricing based. So what we would like to do is to have some sort of pricing based protocol. So the social welfare, the guy with the social welfare function can not only find this allocation, but also say, okay, here are the prices which justify this allocation. Okay? So we don't want to start from a specific state. We want to be able to handle flows arriving and leaving. And so the goal is to obtain a protocol where the dual prices and the primal update rules are defined everywhere. You don't have to start from this very specific state where everyone starts with 0. Okay? And so the approach here is to reinterpret the primal-dual algorithm. And here's my way of reinterpreting. Think of it in the bandwidth allocation context as opposed to the cake context for a second. And imagine that you have 4 flows sharing a 1 gigabit per second link, right? And the first guy is getting 100, the second guy is getting 200, the third guy is getting 300, and the fourth guy is getting 400 Mbps. So together they're using up the whole link. So the dual price computation. So if you want to price for fairness, the way to do it is that in the dual price computation, use simple exponential costs as before, but with different link occupancy values lambda for different flows. So if you look at this guy x1, he'll say, so the link occupancy is, this link is completely occupied, so it look really expensive. But the guy who's using x1 equal to 100 will say my fair share is 250. I'm only using 100 and you're still telling me that this link is too expensive, right? That's not fair. So somehow you want to, so intuitively what we want to say for flow 1, we're going to pretend that x1 equals x2 equals x3 equal to x4 equals 100. Okay? So flow 1 will say, okay, sure, you're giving 400 to x4, but don't charge that cost to me because I'm only getting 100. So for flow 1, you have to pretend that x1 equals x2 equal to x3 equal to x4 equal to 100. So the lambda is 0.4. So for flow 1, it looks like only 40% of the link is utilized. And so this cost is going to be a mu to the power 0.4, and since this is exponential, the cost is essentially going to be 0. So even though the link is completely utilized, it will look almost free to flow 1. Flow 2 will say, okay, x1 is getting 100, I'm getting 200, so for 3 and 4 you can only charge 200, you can only tell me that they're using 200, I don't care if you're giving them more. So lambda will be 0.7, the price will be a mu to the power 0.7. The third guy will see 100, 200, 300 and 300. And so the price will be a mu to the power 0.9, and the fourth guy will see the whole cost. And so for the fourth guy, the link will look very expensive. So in the context of real networks, this corresponds to per flow state, right? So everything else is still the same as before. Every link is still maintaining a dual price. You can still communicate this dual price to the primal agents. Right? So the way these distributed algorithms are envisaged in practice is that the source is sending some flow to the destination. As you're sending the flow to the destination, there's some field, the header field in the packet, like in the TCP packet. And on that field, you're adding up all the costs as you're going from the source to the destination, right? So that's exactly the same thing works now, except that this router or this link is now has to maintain per flow state. So it has to know what everyone's cost is, right? So this pricing. So I gave this pricing scheme for fairness, but it only works if the router can maintain per flow state. And what that means in the cake example is that every cake has to remember how much of it was eaten by which guy. So here's how the primal updates work. If you have this per flow state or this pricing for fairness, the same idea as before. The idea is now you want to be able to start from any state. So if your total dual price is less than 1, you increase xi. If your total dual price is bigger than 1, you decrease xi. But this total price is now computed in this fair way. Right? And one example rule of doing this is saying dxi over dt is minus log of wi. If wi is bigger than 1, it will decrease. If wi is smaller than 1, it will increase. And this is simple enough to be the basis of a TCP-like protocol. So for those of you who have seen like any papers by say Kelly or Low and et al., they write down rules for dxi by dt, which are actually at least as complicated as this. Right? But at equilibrium, if this thing gets into equilibrium, and we can prove there's a unique equilibrium, and if this gets into equilibrium, then for all canonical utility functions, you'll have u alpha x is equal to uy. For all feasible y and with alpha equal to order log n. So essentially you get the same, this pricing based algorithm gives you the same guarantee as the original distributed algorithm and the centralized algorithm and so on, right? And in fact recently we managed to show that it also converges pretty fast. So this was essentially the goal from a bandwidth allocation point of view, to come up with something which is as simple as TCP and which is like simple enough compared to say, as simple as say the Kelly schemes or the Low Peterson-Wang schemes, but which is essentially good for all objectives. And different versions of TCP optimize different utility functions. So this is essentially like saying I can give you a single version of TCP, which is good for all utility functions. Okay. So I'm done with the first concrete illustration. How much time do I have? Like 5 minutes, 10 minutes? Okay. If I have 10, then I can do one more, or I can just stop. If you will have questions, I can just stop. Otherwise, I can do one more. Okay, so let me do one more. So what is the problem is non-convex, right? So the simplest example of a non-convex problem is that you have some integer programming problem, right? So the general paradigm, so then there are no general tools, right? But you have to have problem specific tools, but the general paradigm is something which is very, just along the lines of standard approximation algorithms. You take the integer programming formulation, and then you take a linear relaxation, then you find alpha star and x star for the linear relaxation, and then you round out x star to obtain integer solution. I mean, this is what you would do for any problem which is too hard, and there's no reason why you shouldn't be able to do something similar for majorization. And of course, it won't work in general, but integer programs and rounding techniques are already known for several problems, and you can try to apply them to different cases. Right? And this works for several routing and scheduling and facility location problems, and I'm going to just show you one of those. Yeah. So imagine you're given m machines and you're given n jobs. And job I has a size xi and specifies a set of feasible machines si. So the ith job has some size and can only go on a certain number of machines, right, on this set of machines. and our goal is to assign these jobs to machines, and Lj is the load on machine j. So our goal is to find the allocation of the alpha balance for the smallest possible alpha. So why are we looking at balance now? In the context of load balancing, you want to minimize the maximum load. You don't want to, in the context of resource allocation, you want to maximize what the poorest guy gets. In the context of load balancing, you want to minimize what the most loaded machine gets. But then you also want to maximize what the 2 most loaded machines get together, and then what the 3 most loaded machines get together, and so on. That's the natural analog of fairness for machine scheduling. And so the goal is to find the allocation which is alpha balance for the smallest possible alpha, and that turns out to be NP hard. And so we also know that alpha star is bigger than 1, right? And so we want to give an approximation algorithm for alpha star. So the first thing to do is to reduce this to identical job sizes. So if job sizes are identical, then Kleinberg, Rabani, and Tardosh prove that alpha star is 1. Okay? And someone asked this question earlier that said that essentially the only time you can have alpha star equal to 1 is when everything is symmetric. Right? Here that's not true. Right? The problem is not symmetric because different job A might come and say I can only go on machines 1 and 3, and job B might come and say I can only go on machines 2, 8, and 10. Right? So the set of problems here is not the set here is not the set of constraints is not symmetric, right? And the solution that you will end up getting is not going to be symmetric. Some machines are going to be, if there are 20 jobs which can only go on machine 1 will have a large load, right? But you can still obtain alpha star equal to 1. So now, okay, so it works for identical job sizes. What happens if you have arbitrary sizes? So the obvious thing to do is to use the above as a subroutine. So let me assume that xi, which is the size of job I, is an integer. So I'm going to replace job I with xi jobs of size 1, okay, and the same feasibility set. And then all jobs in the new instance which originate from job I are colored I. So I'm going to somehow remember where these small short jobs came from. And then I can use the LP to find the fractional most balanced vector alpha equal to 1. Okay? And the reason alpha is going to be equal to 1 is because of Kleinberg, Rabani, and Tardosh. So I'm going to use the LP to find the fractional most balanced vector. And now we need to aggregate jobs from the same color onto the same machine. Okay? So here's what a solution might look like. This might be a solution with alpha equal to 1, but it's fractional. So these blue jobs, 2 of them are, light blue jobs, 2 of them are here and 3 of them are here. The yellow are 3 here and 1 here. The red are split across 3 machines, and then you have the purple across these 2 machines and the dark blue across these 3 machines. And somehow, in order to reduce this to a good solution of the integer problem, I have to somehow aggregate these same color jobs. Okay? So how do you aggregate jobs of the same color? You construct a graph with a vertex for each machine, and then you add an edge of color I between 2 machines if both machines have a job of color I. Okay? And then you want to transform this solution so there's only one edge between any 2 machines. Okay? So imagine that there are 2 edges between a machine. So there's a red edge between these machines and a blue edge. Right? Then you can send some red flow here and some blue flow there till one of these edges breaks. Okay? And when this edge breaks, you have not changed the load on any machine, right? Because you send one red here and one blue there, and therefore the alpha is still 1. Then you look at eliminate multichromatic cycles. So let's look at a cycle where there are edges of 2 different colors along the cycle. So what we'll do is we'll start sending red flow from here to here, green here, and blue there, and ultimately we'll end up breaking one of the edges. Right? So we can eliminate all multichromatic cycles. So what will we have if we eliminate all multichromatic cycles and every edge is only one, between any 2 machines there's only one edge? We'll end up having a tree of monochromatic cliques. And so what we can do is push jobs down the tree so that each machine gets at most one extra original job. And this is equal to the Schmois-Tardosh rounding. If you don't know what that is, it doesn't matter. This is exactly it. You push jobs down the tree so that each machine gets at most one extra original job. And the result is a 2 balanced allocation. Okay? And this was independently observed by Azar et al. In 2002 in the context of all norms approximation algorithms. And so the consequence is that for any non-decreasing symmetric convex function f, we have a resource augmented 2 approximation. So f of L by 2 is less than or equal to f star. Right? And as before, the key thing is you don't actually have to know f. So for all, what this means is for any measure you have of unfairness, you are at most half as unfair in some sense. Right? And so as an example, this is a 2 approximation for LP norms, which is essentially what Azar et al. Proved in 2002. And then I'm going to skip the final problem. There are some connections to stochastic optimization. So you can somehow, there's a notion of random variables being majorized by each other, and you can somehow use that for doing load balancing when these job sizes are stochastic. So open problems. So the open problems are, the general paradigm is, are there more practical applications, right? But as far as the first application which I gave, which is pricing for fairness, the main question is, can you remove the per flow state? I don't actually think so, and I think this is there's this big push going on in the networking community where they want to rethink how the internet is designed, and so I think this is the kind of trade-off which they should be thinking about, right? If you have per flow state, so everyone wants to maintain per flow state, but there are no good concrete examples saying, okay, if you could do per flow state, this is what you could do, which is radically different, which you couldn't do earlier. And I think this might be one of those things, which if you have per flow state, then you can say you can have a simple TCP, which is log and approximate for all utility functions. You don't have to worry about what your utility function is, right? And for that you need the per flow state, right? But to be able to make that statement, there has to be some sort of a lower bound which says what I did with per flow state, you couldn't have done without per flow state. So I somehow think it's an important question to figure out the answer to. And then the convergence time and the stability analysis of the simple protocol which I gave, we made some partial progress, but it's not yet solved. And the other thing is heterogeneous user preferences. So if the user preferences are heterogeneous like they are in the Kelly case, can you still, but then they are aggregated by means of this canonical utility function or social welfare function. Then can you still use similar techniques to obtain approximate majorization? And if you could, then that would really start subsuming completely, say, the Kelly law approach. Yeah, thank you.